Many materials we've never heard of have become essential to modern technology. As important as they are in our lives, getting access to those materials can be complicated by social and political factors.
Check these out. It's hard to imagine walking or running with these heavy relics wrapped around your head. So what has allowed us to shed these in favor of these? Magnetism. The big headphones and the little earbuds have one thing in common: magnets. What's different is the type and size of the magnetic material in each. The earbuds use a rare earth element to enhance the magnetic fields, enabling them to be much smaller. Rare earths are in the things you use every day, like cell phones, LED lights, household appliances, plasma TVs, computers, hybrid cars, and catalytic converters. They are in industrial products too, like wind power generators, industrial motors, and MRI machines. The military is also highly dependent on rare earths for night vision goggles, laser rangefinders, precision-guided weapons, and stealth technology. Oh! Rare earths are becoming even more essential to green energy technologies, helping to reduce our global carbon footprint.
This is Pugh Hall at the University of Florida campus, and it is a green building, and it's LEED certified, which means it meets certain criteria for sustainability. Having green, sustainable technologies such as energy efficient lights, energy efficient heating. They're dependent on rare earth elements, and it's these rare earth elements that make them more effective, make them more efficient, make us less reliant on fossil fuels, reduce our carbon footprint. You might have compact fluorescent light bulbs, you might have LED monitors, plasma TVs, those kinds of things that use rare earth elements.
Here's the thing, rare earths are not rare at all, at least in the sense of being scarce. In fact, the rarest rare earth is nearly 200 times more abundant than gold. But you won't find a nugget of a rare earth. Instead, these elements are scattered in tiny amounts. A handful of dirt from your backyard might contain only a few parts per million or even billion of one or more rare earth elements.
They are so scattered on the Earth's surface that you always mine them in conjunction with mining something else. So there has to be a market demand for the something else. For instance, iron is mined, and as a byproduct, you can get rare earth elements. But it's inefficient to just go out and mine a particular rare earth element. They are byproducts with other metals in the earth. And then you have to, of course, extract them and use them. So it's difficult to acquire rare earth elements.
Modern science has classified 17 different rare earth elements. Most of them form the lanthanide series near the bottom of the periodic table. They also include yttrium and scandium. The rare earth elements tend to occur in the same ore deposits, and they exhibit similar chemical properties. Their close grouping in the periodic table is a clue to how chemically similar they are, so it's frustrating for scientists trying to isolate them. But we have figured out many different things we can do with them once they are separated.
They have a number of unique properties. We use them for catalysts, for chemical reactions, but we use them a lot for magnetic structures, in terms of magnetic structures, in terms of luminescent catalytic applications and medical applications. So they're very unique materials.
So one of the things you mentioned was luminescence. So that means these have some unique optical properties. Where do we use those?
Today we make doped material with the rare earths, and they give us the different colors for some of the flat panel displays, like plasma displays, for example. This would be the photoluminescence from mercury discharge lamp, of zinc sulfide doped with silver, zinc sulfide doped with copper, and yttrium aluminum oxysulfide doped with europium. Yttrium and europium being the rare earths, of course. And so we go from a transition metal oxide, transition metal phosphor to a rare earth phosphor here because of the quality of the red light emitted from the yttrium oxysulfide europium.
So beyond lighting, what do you think the next consumer application involving rare earths might be?
I think medicine is a dominant one. Certainly we have a number of illustrations for that. We, for example, know that if you take gadolinium,
MRI contrast agent.
MRI contrast agent, it's excellent for that. You can take and put rare earth dopants into nanospheres, and we can pass the blood-brain barrier with them and incorporate that into detection of brain tumors. And in addition to that, the magnetic applications are very unique because they're very strong. So here's an example of a cobalt iron magnet, and they're not very difficult to pull apart. They're relatively easy, but if you take and add samarium to cobalt and make a cobalt samarium material, they're much more difficult to pull apart. So I'm going to take this here and put that together, and it's going to align the north-south poles, so now you can take them apart for us. And so it's a little bit more difficult, but not very difficult. But finally, let me do this. I'm going to put two samarium cobalt magnets together, and now see if you can pull those apart. Much more difficult. So that's
Strong.
When you have a wind turbine, how it works is you have the blades of a wind turbine rotate at about 15 to 20 rotations per minute, and this rotates a shaft, which in turn is connected to a gearbox and the generator, and the gearbox basically makes those 15 to 20 rotations into 1800 rotations if it's a 1 megawatt turbine, and that generates the electricity. The rare earths, what you do is you come up with, instead of the gearbox, you use direct drive technology, which reduces complexity, it reduces cost, and it also makes it lighter. So you get a more efficient turbine by utilizing these rare earth magnet-derived permanent magnets. Rare earths are cost-effective by doing basically two different things. One of them is it makes the system less complex. So like compared to a gearbox, now you have a direct drive, and so the system is less complex, and so it's easier. And the second one is the maintainability. So once it's easier to maintain compared to a gearbox, where you need constant maintenance, and that's a problem. And especially when you're in a difficult terrain like offshore, it becomes very difficult, and your costs increase.
ArcsPax makes and sells hover engines and hover systems, any size, from small to the large for any application. And what that really enables are a whole group of new capabilities. We can look at it in terms of existing markets, whether we're talking about transportation, structural isolation, obviously entertainment and recreation, education, and probably the biggest is industrial automation. Rare earths, neodymium in particular, is a key component in what is today the most powerful permanent magnet you can make.
So this is the most general form of our hover technology. And what is going on here, there are 4 engines inside this box, and when I turn the box on, they are going to generate a dynamic magnetic field. And when you have a magnetic field in proximity to a conductive surface, and this material that it's on right now is copper, it creates an electric circuit in that copper, and then that in turn creates another magnetic field. So we have magnetic fields in the box, and we have magnetic fields in the conductive surface, and they repel each other, and that's what generates lift. Neat little thing. Hoverboard is certainly an obvious choice for magnetic levitation, transportation, trains, personal vehicles, industrial applications, moving materials handling in warehouse, moving things from point A to point B. It's quite a long list. The fact that we're not limited to linear motion, that we have 3-axis motion with our hover technology. We can move forward, backward, left, right, spin. We don't have to stay on a track. That's kind of special and very unique to how we're generating our magnetic levitation.
If you look at a process that helped build this country, Henry Ford's assembly line, it is by its very nature a linear process. And because it's linear, it is limited. It can be interrupted at any point to disrupt the entire process. Imagine redefining how things are made, where it's not just going from point A to point B, but what if point A and B, if time is the most precious commodity, meet in the middle and then proceed someplace else where they want to go to get the operator, the equipment, and the object that they're working on at the right place in time and space. So we go from an assembly line to an assembly network, and that's the kind of potential we're looking at. The rules are different now. You don't have to touch the ground. We are working with NASA Langley for what will be the world's first tractor beam. It is essentially a way for microsatellites, CubeSats, to be linked in space. And as you know, most spacecraft are aluminum skinned, and aluminum is one of those materials that we can create magnetic currents in order to manipulate them without touching them. And that's special. As a builder, as an architect, I have sworn to help uphold the health, safety, and welfare of the public through the built environment. With the early warning system that has been developed by UC Berkeley in conjunction with Caltech and the University of Washington, every fault in California has been censored. And so when there is a seismic event, that triggers the system. And so at the speed of light, we receive a warning.
Earthquake, weak, shaking, expected in 12 seconds.
The primary waves travel 1.4 times faster than the secondary waves. The secondary waves are what cause all the shaking and the damage and destruction during an earthquake. And so by having those few seconds of warning, most people could, take the time to get out of the building, duck and cover. So in our case, we could use that early warning to activate the hover technology to isolate a piece of equipment or an operating room or even potentially someday a whole building in the event of an earthquake.
Whether 2 seconds or 2 minutes, we have adequate time to activate our hover systems to either lift landing gear or have the support structure fall away. But the point is that the object doesn't move. The object doesn't move, but we get the early warning, the supports fall away, the ground shakes, the shaking stops, the supports return or the landing gear drops, and that object never moved. This is the first possibility for a perfect seismic isolation. Corrosion, you think about it in terms of the degradation of infrastructure. Right now, to detect corrosion, it's a really expensive proposition. Magnetic field architecture may be able to offer a more efficient way of detection through eddy current and some other means.
So with all of these current and potential uses, rare earths will continue to be valuable. And from the map, it looks like they are scattered all over the globe. But moving them from mines to manufacturers is not easy. Politics and commodity markets get in the way.
The world was supplied from a number of different countries with the rare earths back in the 1990s, but China made a conscious effort to dominate the market. They now dominate the market to 96 or 98%.
Well, there's a lot of challenges. One of the things is to develop substitute chemistries. In other words, if there's a use of a certain rare earth element and it's difficult to acquire, can you figure out how to use a different rare earth element as a substitute for it? Or if we need a certain element to make wind turbines, which are so important for our green technologies, our wind technologies, but they need a rare earth element. Can you design them in such a way that they need less of that, or that they could use a substitute element? So I think the challenges are for engineers to realize the political and economic realities of trying to acquire this very important raw material.
We've got a hovering box, and our big thing is, what on earth can we do with this? And we've come up with a bunch of things. We listed them all out. And then when we announced it to the public, people came in with all these crazy ideas that we had never even thought of, and we're just like, whoa, we're not experts in these areas, but suddenly people are coming to us and saying, I've seen this hover technology, we could totally use this in this application, and how and where do we go from here?
We cannot go back. We cannot go back to where we were before. There will always be more and more demand for rare earth elements. And so we have to be creative, we have to be realistic about how we can acquire these, how we can use them in sustainable ways for our future.
We are already dependent upon rare earths in many important parts of our lives. As demand grows, how do we balance the politics of obtaining them with their powerful potential?